Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we started our discussion on this particular technique, multiple linear regression. So we discussed the linear regression, the equation, the different coefficients that we are required to estimate. We talked about the explanatory modeling and the predictive modeling, a few differences, and we also tried to understand the application of this particular technique, multiple linear regression, in a statistical technique and how it is different in a data mining environment. So we also talked about some of the assumptions that when we apply OLS to estimate those coefficients, those beta zeros and sigma, then what are the underlying assumptions that we have to follow, and how those assumptions are different. How first assumption, especially noise following normal distribution, how we get some relaxation from that assumption in a data mining setting. We talked about all those things. Then we'll again go through an exercise to understand how linear regression modeling is done and how different concepts can be put into practice. So let's open RStudio. So as usual, we'll load this particular library XLSX, because the data that this particular data used cars data set that we have, it's in the Excel file. So let's import this data set. So the function that we are going to use is read.xls. First argument is, as usual, we are going to browse for this particular file, and then the first worksheet will import the data of the first worksheet, and the header is true because we have name of all the variables there in the data set. So let's execute this line. You can see in the environment section this particular data set has been imported, and you can see 79 observations of 11 variables. Let's have a look at this data in the R environment. So this small icon that you see in the environment section, once the data has been imported, so once you click on this particular icon, you would be able to see another tab that would open, and you would be able to see the data just like you see it in the Excel files. So you can see the variable names, brand, models, manufacturing year, fuel type. So there are 3 fuel types for these used cars: petrol, diesel, CNG, and then we have showroom price for each of these used cars. So when these cars were bought, first time bought, these right, as the new cars, so what was the price, and then the kilometers since these cars have been running on road, the kilometers that have been accumulated from the starting years, from the purchase year, and then the price. This particular price is the offered price for these used cars. The cars, whether the transmission is manual or automatic, that is also we have information on. So 0 representing the manual and 1 representing the automatic transmission. Now next variable is on owners, where each number is representing the number of owners that actually owned, the number of people, number of individuals who actually owned this particular car. So that is also there. We also have information on some of the security features, for example airbags. So number of airbags that are there in the car, so that information is also available. We have another variable in the data set, that is C price. This variable is generally present for the classification task, where any car having a less than offered value of 4 lakhs is represented by 0, and the cars having value of equal to or more than 4 lakhs are represented by 1. So this is the data set. So let's close this particular tab. and let's so first thing would be, as usual, we would like to remove the NA columns. So we use these within the brackets in the for the column value. So we have applied this particular function. So apply, what it is going to do is it will find out using is.na function will find out which of the columns in this particular data frame df they are having NA values, right. Those particular columns would be selected. So 2 is indicating that this particular function is being applied column wise on this particular data frame. So therefore those particular columns, NA columns, would be selected, and the all function would then be applied on those columns. So other columns which don't have any values, they would be true, and then the columns which have any values which will have false values. A logical vector would be returned from this function, and then we have this another operator not that would apply on this logical vector, logical result, and then all the true values would be converted into false, and all the false values would be converted into true. So therefore all the NA columns which were identified using the apply function and they were indicated as false, now they would become the reverse will happen. So all the columns which don't have NA values, they would be returned as false using apply function, and when not is applied, then they would become true, and the other columns, they would be returned as true because they were NA columns, and when not is applied, they will become false. So those columns would actually be dropped. So this is how this particular line we have been using quite often. So this is how it will operate. So in this particular data set, we didn't have any such columns, so the result would remain same. Now let's look at the first 6 observation of this particular data set. You can see they name these variables as we saw through other options in RStudio by clicking this particular icon and looking at the full file in one go. So using head function, we can look at the 6 observation. We need not look at all the observations, that would require the whole file to be loaded into memory, and therefore if your device where you are running your RStudio and if it doesn't have sufficient RAM built into it, then probably you are better off running head function, and you would just be loading 6 observations into memory. So so these are the observations, the variables we have already discussed. So one particular third column that we can see is manufacturing year, when the car was actually manufactured. So the age of car can actually be computed using this particular vector. So this is what we are going to do next. So you can see age variable, and if these offered prices, if all the information is in the context of year 2017, so therefore the current year is 2017, so we can subtract all this particular vector from 2017, and all the values, all the observation, for all the observation will get the difference and therefore the age. So let's execute this line. You can see in the environment section, age variable has been created, this numeric vector having 79 values, right. So age of all the used cars have been computed. Now age could be a relevant variable, because as we discussed, the task here is the prediction task. We would be trying to build a model, we will build a model to predict the price of a used car, right, offered the price of a used car. So age could be an important variable in terms of explaining, in terms of predicting that particular price. So therefore we would like to have age also in our model. So let's append this particular variable, this particular vector in this data frame. So cbind is the function, as we have talked about in previous lectures also. This can be used to an already existing data frame to append this particular variable. By default, it would append this variable at the end of all other columns in this data frame. So let's execute this line. So now this particular variable has been appended. If you want to check again, you can run the head, you can call the head function again, and you would see the last column age has been created, and you can also see the values for first 6 observations. Now if we look at this particular data set, then brand name, first 2 columns, brand name, model, and also third one also manufacturing year, they don't seem to be relevant for our analysis. For a manufacturing year, we have already transformed this particular variable into an age variable, age of the used car. So therefore we won't be requiring this particular variable, right? So we'll get rid of this variable. Also since we would be building a prediction model, so therefore this C underscore price, which was the outcome variable mainly designed for the classification task, we also would not be requiring this variable. So we can get rid of these 4 variables, first one brand, then model, then manufacturing year, and then this one C price, and the remaining variables would be either outcome variable, that is price, or the relevant predictors that we want to include in our model. So first let's take a backup of the existing data frame. So let's take a backup. You can see this this particular data frame has been created. Now let's eliminate these columns. So combine function can be used, and minus before combine function indicating that we don't want to, the subset that we want is other columns that are mentioned here in the combine function. So if we want to have a look at, now if we are interested, we can have a look at the structure of the data frame. Now in the present data frame, this data frame that we have is we have all the variables of interest. You can see now we have 79 observation of 8 variables. So all the variables are now of interest to us for our modeling exercise. So fuel type, right, that would also help us determine the price of a used car, because the CNG, whether the car is running on a CNG fuel or diesel or petrol. So these cars are when they are purchased for the first time, they are priced differently, and therefore depreciation and other factors, they work differently. Therefore prices of these cars based on the fuel type that they have are going to be different. Therefore fuel type being an important predictor for us in this prediction modeling exercise. Now SR price is actually the showroom price. So this is equivalent of similar to the first time, when the first time this particular that particular car was purchased, what was the price that was paid, right? This is the price. Over the years the depreciation would be applied, and the depending on the condition of the car and other variables, some of those variables we have in this data set as well, the offered price would be adjusted. Now how this offered price is being determined by the individual is part of this exercise of this model. Now the another important variable that we have is km. So the number of kilometers that a car has accumulated, that also tells about the wear and tear that the car might have gone through because of those number of kilometers covered, right? So therefore kilometer might also indicate the value of a car that is that should be depreciated, that should become part of the depreciation. If the car has been driven less, then probably it has not gone through that much of wear and tear. But if it has traveled more, then probably more wear and tear might have happened, and therefore the price might be on the lower side. Therefore kilometer is also an important variable in this exercise. Price is the variable, the offered price, that is the variable that we are trying to predict. This is the outcome variable of interest to us. Next variable that we have is transmission. So, transmission right now as indicated in this output, this is right now numerical vector as shown here, but this variable can have only two values, or let us say two labels, because this is a categorical variable, because we have just two labels, whether the car is automatic or the car is manual. But here in this data set it is being shown in, it is a numeric vector here, zeros and ones. So, we would like to convert this vector from numeric to categorical variable to factor variable. So, therefore, you can see in the next line we have used as dot factor function to coerce this particular numeric variable into a factor variable in our environment, because this variable has two labels, two categories, that is the car is automatic or manual. So, let us execute this particular code, and once it is done we can again run this structure function, and you would see a change there. The transmission variable, now you can see it has been converted into a factor variable with two labels 0 and 1. So, now the value 0 and 1, they are being treated appropriately, because this being a categorical variable. So, now these values have become numeric codes indicating two different labels. Now, in the structure function you would also see that some few initial observations that are being shown here, they are in this format 1, category 1, category 2, 1 and then 2 and then 1. But the actual values as we had saw before in the using the head function, they are either 0 and 1. So, this is just the way output of a structure function is presented. The values haven't changed because of that conversion that we just did. If you are interested, you can again have a look at the actual values. You can see the transmission variable is still having the same 0 and 1 values. It is only the structure function that is presenting the output in that fashion, that for factor variables, if for factor variables it generally shows 1, 2 and 3 for different categories, different labels that we might have. You can see even for the fuel type variable, CNG, diesel and petrol, these are the three labels that we had. In the structure output we see 3, 2, 3. So, these representing the three classes 1, 2 and 3, but actual values are same, they are not disturbed. So, you can see fuel type, you can see these strings, these characters petrol, diesel, and therefore, those values are not changed. It is just the representation in the output of the structure function. Now, another important thing that we need to understand here is that the factor variables that we see, they are nominal variables. The way they have been created, these are nominal variables, these are not ordinal, and the way labeling is done here, for example, if we check we run the df function for the first variable, that is fuel type, you would see these values, first 6 values, petrol, diesel, petrol and petrol, all, and then labels CNG, diesel and petrol. These labeling in our environment is done alphabetically. Therefore, CNG, because it starts with C, which is and then diesel, it starts with D, then petrol P. So, the alphabetical in a alphabetical fashion, the ordering of labels is in that fashion. But when we when we run a classification task, we will have to decide our reference category. So, in that case, if we happen to select our reference category as petrol, that won't be by default made as the reference category here in this case. We will have to relabel this variable. So, this kind of exercise we will do when we discuss a particular technique that is suitable for classification or used for classification. So, next thing that would be required. So, once we have done all variable transformation, we have checked the variable type, appropriately transformed them. Now all the variables are ready and we are ready for the modeling exercise. So before we go ahead, we need to partition this particular sample. So in this particular exercise, we will partition this particular data set into 60% for the training set and the 40% for the test set. So we won't be having a validation set. We would be building our model on the training set, and then we would be testing our model on the this test partition. So sample is the function that could be used to perform this partitioning. So in the first argument, as we have discussed before, we need to specify in a numeric vector form the number of observations. So in this case 1 to number of rows that are there in this particular data frame, representing the number of observations that are there in the data frame. So that being indicated, then the size of the sample, that is being indicated by this 0.6 into the length of the data frame. So because we want 60% of the observation to randomly selected observations to go into our training partition. So therefore 0.6 into this the full size, and the replacement is false because we want to do our sampling without replacement, which is the typical way of sampling in a modeling exercise. So this particular sample function would return us the indices of those observations which have been randomly drawn. Now to further partition, so let's execute this line. So you would see that part IDX, this index variable has been created. This is integer because these are the indices that have been returned by the sample function, and you would see that 60% of the observation, the indices of 60% of the observation randomly drawn from that particular data set have been returned. Now we need to partition the data set. So we can do using these brackets functions, we can subset these particular observations from the full data set. So in the rows value, for the row value within the brackets, we can mention this particular variable, and all those indices would then be subsetted for training partition. So let's execute this code. So we have been able to create df train. You can see 47 observations of 8 variables, which is same as the part IDX, which was also 47, which had 47 indices in the first place. Now since we are creating just 2 partitions, therefore all the remaining observation can go through, can actually be left for the test partition. So within the brackets, in the for the row value, we can mention minus part IDX. So the remaining indices, they would be subsetted for the test partition, df test. So let's execute this code. Now once the partitioning exercise is over, now you can see in the environment section, df test, another partition has been created having 32 observations of 8 variables. Now once this partitioning exercise has been done, the function, we can move to our linear modeling, linear regression modeling. So the function that is available in R to perform this modeling is lm. If you are interested in finding more details about this particular function, you can go to the help section and type lm and enter, and you would see that in the help section it talks about this particular function. lm is about fitting linear models. So you can see in the description that it talks about that lm is used to fit linear models. It can be used to carry out regression, single stratum analysis of variance, analysis of covariance, right. So all those statistical tests can be performed using this function. Now if you look at the usage, you can look at the function and the arguments that can be passed. The first one is a formula that is going to represent the linear regression model, right. So we need to pass this particular formula, and then the second important variable is data. So there are many other arguments also. So you can, on your own time, you can go through some of these variables which are not typically used. So the formula is written in this particular format. So the outcome variable of interest, it is written first, and then we use the tilde operator, and then we can write all the names of the predictors that we have in our data set, and that we want the variables predictors that which we want to include in our model. Or we can simply type dot if we want to include all the variables that are available in the data set. So if you remember, then the data frame that we are using now, that we partitioned, we had already excluded the variables that we did not want in the first place, and therefore all the remaining variables are come into our set of predictors, and we would like to have all of them in our model. So our formula is going to be price tilde dot indicating to this function that all other variables should be part of the set of predictors. Now the data set that we are using is df10, that is the training partition. So we would be building this model on training partition. So let's execute this line, and you would see that in the environment section a mod variable has been created. If you are in, so it is this particular variable is actually a list of 3, so it has information on 13 elements. If you are interested in finding out all the names of this particular list, you can run names command. So these are the 13 elements that are there. You can see the first one is about coefficients, then second one is about residuals, then effects, rank, fitted values, assignment. Similarly, so many other details have been computed by this particular function. If you are interested in finding out all these values, you can again go to the help section and find out, and scroll down in this particular section, and you would see that there is going to be discussion under the value subsection, the kind of values that are returned by lm function, and within this you will have details. What are coefficients? The coefficient, a named vector of coefficients, so the coefficient that we have, residuals, fitted values. So details about all these returned values would be there. So we might not be interested in all these returned values. So summary is one important function for us to get the relevant output from this exercise. So let's execute this. So let's look at the summary output. So you can see that the call explaining the formula that we had given there, that we have the arguments that we have given to the lm function. Then we have residuals, some descriptive statistics about the residuals. You can see that minimum value, median value, this particular residual is of this models are having, mean, max, median, first quartile, third quartile. Now let's come to the important part that we would like to discuss first, coefficients. So the coefficients you can see for all the predictors are we can see here. First one is the intercept, that is the constant. So this particular estimate is representing the beta 0 that we had in our slide. So this particular intercept against intercept, this particular value that we have, this is beta 0. The corresponding standard error for this particular estimate is also given there. The t value and p value have the same meaning which we described in our supplementary lecture on introduction to basic statistics, right. So those values remain same. We have also discussed a few more details about these values there, so you can watch those particular lectures. Now the next important variable that we can see is fuel type. Now you would see that instead of one we have two variables for fuel type diesel and fuel type petrol. Why this has happened is because fuel type is a categorical variable and it had 3 categories. So for all those categories, because the way softwares are implemented, the way these techniques are implemented, they cannot handle the textual data, and therefore dummy coding has to be performed on these variables, categorical variables, and depending on the number of categories in a categorical variable, we will have to create equal number of dummy variables. So dummy variables are actually representing different categories. So for example, fuel type, we had 3 categories: diesel, petrol and CNG. So for each of these categories, right, diesel, petrol and CNG, so we had these 3 labels for fuel type. For fuel type labels, so for each of these labels we will have to create dummy variables. So dummy variables would indicate presence or absence of that particular value, that particular label. So if the value is 1, that means that car is having fuel type of diesel. If the value is 0, that means that car is not having fuel type of diesel. Similarly, the variable, the dummy variable, corresponding dummy variable for petrol having value 1 will mean that the car is running on the fuel type of petrol, and if it is 0, it is not running on fuel type petrol. Similarly for this one. So therefore for each label we will have to create equal number of dummy variables. So we will have 3 variables. So for the fuel type, instead of having 1 variable in our model, we will end up with 3 dummy variables to represent this particular categorical variable. But if we look at the variables, presence of if we have information on 2 variables, any 2 variables out of 3, if we have these any 2 variables out of these 3, then the other variables information is automatically known. So therefore in our modeling exercise, right, if a particular value is if a particular car is not having diesel or petrol, then of course it will have CNG. So because of that, if we have information on 2 dummy variables, the third one is automatically known. So therefore in our model we just have to include 2 dummy variables. So if there are n classes, then we will have to include n minus 1 dummy variables in the model. Now what happens to the remaining label, right? So for example, petrol and diesel are selected here, and we had petrol, diesel and CNG. So the remaining label, it becomes the reference category that we have been talking about. So any results that we get for these 2 variables, now these 2 dummy variables P and D, those results would have to be interpreted with respect to this reference category. More on this, so we will stop here. More on this particular dummy coding we will discuss in our next lecture. Thank you.